if we talk about the radiation that we see from the sun, so it follows a black body spectrum. Okay, and you simply fit a black body spectrum, you can determine the temperature, because in the Planck's equation you have only one variable, which is temperature. Everyone knows it. Fine. So for the sun, this number comes approximately 5,800 Kelvin. This is the peak. This is the peak of the black body radiation. This is the effective temperature considering sun as a black body. If you can calculate the corresponding wavelength for that temperature, it will be like around, you will be getting yellowish orange color. Okay, that's why the sun looks yellow. Now, if we talk about the stellar spectrum, means the spectrum of a star, typically it shows absorption features. This also I have taught. Fine. Everybody knows? Okay. So, and these absorption features are the characteristics of various chemical elements present in the outer atmosphere of that star. You understand the concept? You have like core, when nuclear fusion is taking place, it is emitting continuous radiation throughout. But when the radiation passes through the outer layer, which is very cold, so some of the radiation will be absorbed. Because, and that depends on the what chemical species are present. They will absorb at certain wavelengths, so we will see absorption features. All right. Okay, before we start about these details, let me quickly remind you about the basics of spectroscopy. First, the emission spectrum. What happens when suppose we have a very hot gas? So if you collect the light coming from the hot gas and pass it through a prism, which will divide the light into its constituents. So we will see something called emission spectrum. Hot gas will emit, like hot gas means gas will have some ions, atoms, molecules, etc. Mostly will be ions. Gas will be hot. So these ions will be emitting at certain frequencies. Emission spectrum. Okay? Understood? So this is what we see, and when we plot in the flux versus wavelength scale, this is what we see. Okay? So here you are seeing the emission features, these are emission lines. Fine? For example, this is a magnesium. 2 means first ionization state of magnesium, which you write Mg+. In astronomy, we always give the name of the ions by saying some metal we have magnesium, and if it is doubly ionized, we write with the Roman numerals 3. Okay? Something like Mg 1, 2, 3. This corresponds to Mg++. Everybody understood? So I am telling this is Mg2, which means this is the first ionization state of magnesium. This is carbon 4, corresponds to third ionization state of carbon. Okay? Alright. Now let us talk about the continuous spectrum. So what happens, suppose we have a bulb radiating at all wavelengths. Okay, like the core of the sun emitting radiation at all wavelengths. It does not emit at a certain particular wavelength. It is emitting across the electromagnetic spectrum following the black body law. And when you pass this light through prism, you will see a continuous spectrum. That is, this is what you see. And this shape depends on the temperature of the black body. Okay? Fine. Now third we have absorption spectrum. So suppose there is some source of radiation, but there is some cold gas in between. So it will absorb some of the radiation, and that the absorption will be what this is what we see in the form of absorption lines. Okay? So now everybody understood what is emission spectrum, continuous spectrum, and absorption spectrum. Fine. Now in the case of sun, what happens? This bulb is nothing but sun's interior hot region, the sun's core, where the nuclear fusion is taking place. What is this cold gas? This is the sun's outer cooler region or photosphere. Fine. What is prism? Is our telescope. Basically, an instrument on telescope, not the telescope. A spectrograph. Alright? And that's what, and what we see absorption spectrum from the sun. Basic ideology and everybody understood. Alright. Now, so this I was talking about that a typical stellar spectrum shows absorption features, Now, if we talk about the normal galaxies, can you tell me the name of this galaxy? Andromeda. Fine. So the light from normal galaxies is just the sum of light from all the stars within it. So since the spectrum of a star is predominantly absorption spectrum, and we are seeing the collection of light from all the stars. So collectively, we will be seeing an absorption spectrum. Okay. So this is the spectrum of a normal galaxy. Got the idea? So if some alien will be taking the spectrum of our Milky Way, most likely the alien is going to see this. Fine. Okay. Now I will tell you some history. Long before 1943, earlier actually basically it happened in 1908. For the first time, some scientists they took the spectrum of some galaxies. So they instead of observing absorption lines, they saw emission lines. But that time we were even not knowing that whether are there any other galaxies in the universe other than our Milky Way. So we had no idea about that time. What is this? That time we were thinking that our own galaxy is the only galaxy. Is this the universe? And whatever the huge patches we see in the sky, they are like islands in our galaxy. Just 100 years ago. Okay. Back in 1915, I think 1920s, when Edwin Hubble he calculated the distance of these islands using something called Cepheid variables. I haven't taught you, but if you search in Google Cepheid variable, you will realize what is the history of it. Like these are the stars which pulsates, and their pulse period is very fixed. So this means, and there's something like you can directly calculate the distance from where they are, wherever they are. You can calculate the distance. Fine, okay. Basically, what it does that there is a direct relation between the pulsation and the luminosity, and from luminosity you can calculate the distance if you know the flux. समझ आ गया ना? No? See? I am telling that, okay, let us assume that there is a relation between the pulsation of a star and its luminosity. Fine. You know the relation. So if you calculate the pulse period, you can calculate what is the corresponding luminosity of the star. Fine. Now you observe the star. When you observe the star, you can calculate flux. You know luminosity, you know flux, and you know luminosity equal to flux into area. Area will be 4 by d square because the star is somewhere. It is emitting in a spherical shape everywhere across the radiation. It's like one the star emitting in all the directions. So you want to calculate the luminosity. My luminosity, so you have to calculate my flux multiplied by the spherical area. That's the energy going out. So if you know the luminosity, if you know the flux, you can calculate the d from area. Fine. So we can determine the distance. So when Edwin Hubble, he calculated the distance of these islands, he found the distance are super large. Like larger than what we can think about the size of the Milky Way. So that it was like 1925 sometime. That was the first time it was observationally it was established that these are extra galactic things. Okay. Fine. So that's how slowly this entire story of that there are different galaxies, not only Milky Way. The story started in late 1920s, 30s. So 1943, there was one scientist named Carl Sifford. He was observing some galaxies from Mount Wilson Observatory in United States. Okay. This is what he saw. This is the spectrum of that galaxy. This is what he saw, and that he published. So people were publishing papers in 1940s. This is an old tradition. Einstein also wrote papers on general relativity. It was in German. You can find the original, like his scanned memes, that version of that article which he wrote. Okay. So now the question came that he noticed several broad lines, and this is the image of those galaxies. Like there are like two images you guys. This is the technology that we had that time. Fine. So the question came, how galaxies can emit strong emission lines? We were expecting absorption lines, but how they are swinging? Because you see how broad line is, isn't it? So how suddenly so galaxy can emit strong emission lines? The mystery was there. We did not know. And the more perplexing question was that from where these lines are coming. Means what is that hot gas which is emitting this radiation? That is not present in normal galaxies.
Recording in progress.
Okay. Fine. See, this is what we saw in 1943. This is what we get in 2000s. You got the idea? Okay, now let us start putting the pieces of puzzle together. So we got some information, emission line galaxies. Okay? Now next thing comes, when people started observing such sources, they found that the central region of such galaxies is unusually bright. How bright? That bright that rarely you will be able to see the rest of the galaxy. Okay? Here I show you a picture of a normal galaxy. This is a Hubble Space Telescope picture. Fine. This is a normal galaxy, unlike our Milky Way. Now, if you take a look at those galaxies, peculiar galaxy, you will see something like this. Okay? Can you see the whole galaxy? Who can see the whole galaxy? I want to know. No one can see the whole galaxy. Of course. You see, this means this central region is. See, this. So, in other words, you can think of that this object look like a star. Okay? So basically, what was happening that the central region always like points. So can we have such a like super bright star at the center of that galaxy, which is so bright that it is overshining the rest of the whole galaxy? One more piece of evidence we got. Okay. Then there is a scientist named Martin Schmidt. He just passed away like last year or maybe like 2 years ago. So back in 1960s, he took the spectrum of one such unusual galaxy. So, and this is the spectrum that's what he observed. And then when he compared this spectrum with the lab frame spectrum. Lab frame means when you know the rest frame wavelength of different elements. You know at what wavelength you will be seeing the emission from magnesium line or magnesium plus or magnesium plus plus. Because from the knowledge of our knowledge of chemistry. Okay, like say you know that from ground state to infinite, how much energy we need for the hydrogen atom? 13.6 electron volt. So we know it. Similarly, you can calculate from n equal to 1 to n equal to 3 or n equal to 4 how much energy is needed. That energy corresponds to the line that you will see. So lab frame means we know the rest frame ideal spectrum of the gas. Now when we compare this spectrum with what we observe, okay, so that's what he did, and he found that H beta line, which is supposed to peak somewhere around 4,865 angstrom, it is peaking somewhere around 7,000. It is coming 7,000. Okay, so this means, and not only H beta, several other lines. He is seeing that these lines are systematically shifted towards the redder side. Okay. Then this was like 1960. So this these are another observational information we got that these galaxies sometimes they show red shift. Okay, and when you can calculate the distance from this red shift, because if you have some idea about the cosmological expansion of the universe, so by the time we were doing Hubble extend because Hubble already proposed in late 1920 that universe will expand. Fine. So from this redshift, you can calculate the distance. So when people calculated the distance, means like Martin Schmidt calculated, and the object was named 3C273. This is the 273rd object in the third Cambridge catalog. It's a radio kind of. So the distance, its redshift was 0.158. Basically, what you have to do, you have to multiply the rest frame wavelength of some particular ion by 1 plus z to get where it should be. So this means if I give you the spectrum of some galaxy, you can calculate redshift. If you can see more than one line, if you can see only one line, then how will you? But if you can see more than one line, you can calculate what is the corresponding redshift. This is what we do today also. Fine? Understood? So when he calculated the corresponding distance, it turned out to be around 760 megaparsec. 1 parsec is around 3 into 10 to the power 13 kilometer. So it turned out around 10 to the power 22 kilometer. Okay? Now, so this is another mystery that how they are the mystery that these objects are so distant. The size of our Milky Way is around 30 to 40 kiloparsec. Now you see the distance of this object, 760 megaparsec. Okay, and basically the picture I showed you the below. This is the 3C273, right? Fine. Now let us think something to understand what is going on. Let us think from a perspective of if you are an astronomer in 1960s, and we are getting this information. We have no idea what was that. So let us see a normal picture. Let us focus on two stars, object A and object B in the night sky. Okay, they look similar, right? Isn't it? Fine. Now, if I tell you that object A is located 10 to the power 10 times farther than object B, then you will be surprised. Then the other object even is so far, but it still looks equally bright. So, how much intrinsically that object A will be powerful? How much powerful it will be? Understood? Na? You see, suppose that the case you consider that these are two cars. The car which is even farther away, but it still looks brighter. So this means its headlamp will be more like a very powerful light it is throwing. Got it? You want me to give you another simple example? You know, no, you don't want? Okay, fine. It does not want. Alright. Everybody knows the name of President of the United States. But you know who is the mayor of Atlanta? You don't know. Why? You know more luminous guy. You do not know less luminous guy. The object guy is so distant, but still is so luminous that you can see the radiation. Okay? But he will be knowing who is the chief minister of this state. Everybody knows. It's a nearby. Okay? This F proportional to 1 by d square is the flux proportional to 1 by d square. This means as the distance increases, your flux decreases. Everybody knows inverse square law. Fine? So suppose if A and B look similar bright, this means we are receiving similar flux. So if I tell you that A is located 10 to the power 10 times further away, so you can calculate what will be the corresponding luminosity. Then you will find out that the luminosity of object A is like unimaginably larger than that compared to object B. So the next, once you realize this part, so the next question comes: how it is generating so much power? Isn't it? How it is generating so much power? It's not a joke. If I told you about the sun, that will be like it emits radiation via nuclear fusion. Nuclear fusion will emit some energy. Something. That's what we see in object B. This is a nuclear fusion. But in object A, what is going on? Okay. So then people started giving several hypotheses, models. So that's what we do in astronomy. If we get some observation, so from theory we try to explain it. So that time we got some observations and we had no idea what was going on. So some people gave one idea that probably at the central region of those galaxies, there are lots of supernovae happening all the time. Supernova can emit this much energy. This is fine. This is one plausible explanation. Fine. But you know that supernova activity is a very transient activity. It happens only for a few minutes. And then the emission decays. Okay? नींद आ रहा है? नहीं आ रहा है? ठीक है. I am telling very good story. sleeping, full sleep. Okay. But the point is that when we were observing these objects, we find that they remain that bright for decades. So this means those many supernova events needs to be keep happening for decades. And then you can do a simple mathematical calculation. You know the luminosity of the object, and you know the typical luminosity energy released by one supernova explosion. So you can determine how many supernova explosion you need to produce this much. Okay, this will give you a corresponding how many stars you need, which can undergo supernova. Okay, so then the calculation people did, it turned out to be that the number density of the stars needed in a central region is like unrealistically high. We can't have that because some of these, now I will tell you the names. Some of these galaxies will now later they will be called quasars, which corresponds to quasi-stellar radio sources. These are radio sources means they are bright in the radio band. Quasi-stellar means they look like a star. And that's what the name came quasar. So some of these quasars like CC273, people were observing since late 19th century, means 1860, 1870. That time they thought it's a star, but they were measuring the numbers. Okay, people were doing astronomy for a long time. Aryabhatta, Varam here, one statue outside, you can go and get some impression, appreciation. Fine. Now, so we found that this radiation sustained over centuries. So supernova explosion is was ruled out. It's not possible. That's what we do today. Also, some observation happen, we give some story, and then some other observation we get, and that can rule out some things. So then people will come up with some other story. This happened all the time. That's what we do. Okay. Now, so then there is a couple of scientists who gave this idea that it may not be supernova, it may not be nuclear fusion, it may be something called conversion of gravitational potential energy into radiation. Because people did the theoretical calculation, and it turned out that for the nuclear fusion, the efficiency is 0.7%. This I show. Okay? And for the other process, it turned out the efficiency can be as large as 30%. So 30% of the mass is converted to radiation. It's super efficient. Okay? Now, so this means now this like it didn't happen in one day or 1 year. It took like decades of conferences and meetings and discussion, etc. And then people slowly started coming with the idea that now what is happening that there is a very massive and dense object at the center of those galaxies, and what it does, it swallows the matter. Matter means gas or dust from its surrounding. One cartoon picture you can see here. Okay. So that compact object is somewhere below, somewhere down. Okay, fine. Now, in falling matter forms a disk. This also I have told you. Why it forms a disk? Conservation of angular momentum. Because the matter which is going inside is not simply going radially. It will have some tangential velocity, and because of that, it will form a disk. And the slowly gravity is pulling inwards. It will spirally, it will keep going down towards the center. Okay, so this process is called accretion, and the shape this matter takes, this is a disc shaped structure. This is called accretion disk. Okay, you guys have seen how people make pizza. So they throw something here, and then it spreads up. More or less something like that. Right? All right. But how do we know there is a black hole? Next question. See, that's what we do in astronomy. We do not take anything for granted. We always ask questions. So how do we know there is a black hole? And you know that this name black hole was first coined in 1967. Before that, there was no name, nothing called black hole. In 1967, only somebody gave the name because they didn't think of black hole. I don't know why they didn't say anything else, whatever. Okay, how do you know there is a black hole? So there are observational evidence. I will show you some evidence, but let us see whether first this video works. If it will not work, I will show you some outside. I doubt it will work. It is not working. Okay, then I'll show you video outside. The video is very good. So let us see this video. So before I show you, let me tell you what it is. This is the, you can say, you take the picture of our the central region of our Milky Way. There are stars. So you take some picture today, and then take a picture after some time. So you understand that the position of the stars will not remain same because they are moving. Everything is moving in the universe. Alright. So this video tracks the motion of those stars which are lying in the central region of our own Milky Way. Fine. People got Nobel Prize for this discovery. This finding, I think, last year. This is one of the discoveries. Okay. So you can see all these stars are moving. The stars which are far from that central star, they are moving slow. And as they come closer towards that something central like that star, they move faster. Isn't it? What is that central star shape using? That is not a real observation. That is, I am putting something on top of that. Just to highlight that these stars are orbiting around something in the center. Okay, let us see it again once. You see? So now you see this star which is coming, and you see the first moon. And now you see Eris. You got the idea? So you understand, if you simply apply your Keplerian motion, planetary law with this two body problem. Okay? So if you know the mass of the orbiting star, and if you know their distance to that hypothetical object which you cannot see, like what is the weight, this elliptical orbit, major axis, minor axis, etc., you can calculate the mass of the other body. Isn't it? M1 R1 plus M2 R2 equal to M1 plus M2 into R. Fine. Then you apply condition of angular momentum. So you have two equations, you can solve for mass and you can determine that. Fine. So when people did it, did you notice that there is a time shown in the right top corner? Nobody noticed. Nobody noticed. This video which you shot, this covered the observation of taken over like 25 years. Because they are so distant, their motion will be tiny. So it took us some time to figure out how like slowly they are moving. Though their speed will be like hundreds of thousands of kilometers per second. Okay? So this means there is something very heavy which is not seen, located at that center, around which all these things are orbiting. Okay? Fine? So when people calculated, so that mass turned out to be around 1 million solar mass. Now we do not know any star of 1 million solar mass. So that massive thing can be black hole. Got one observation evidence. Now then more observations started coming. Now everybody knows about all these things. Oh, she is working now. What is this? Fine. Okay. You know, Event Horizon Telescope imaging, direct imaging of central region of one such galaxy called M87. Okay. And then you must have seen this kind of photos. So there is a black hole at the center, super compact. So you see, this observation came in 2018 or 2019. So before we knew black hole from long back. So people did mathematical calculation that if there is a matter surrounding the black hole, if this gas is falling onto the black hole, then what should be the radiation pattern, what should be the structure by applying general relativity, gravity, etc. Okay, so this is what people proposed and this is what we saw. Now I will show you another picture of something sometime later, then we will discuss more about it. So you know that we have one more observation evidence for the presence of black hole. So these pieces of evidence puzzle started giving us more information about the central region of those galaxies. It all started with the observation of emission lines. Fine. This I have already told you, so I will quickly go through it. That suppose there is a central compact object, and this is the, you can say, this is accretion disk. Okay. You understand that different layers will have different velocities because of the different gravitational force they are feeling, because of their different distances. Fine. So the V2 will be greater than V1, everybody knows. V equal to square root of G by R. We can apply our simple Newton's law here because our distance from the central region is very far, very large. We can apply Keplerian motion. General relativity effect, general relativistic effect will be neglected. Now this I have told you, since the velocities are different, so there will be velocity gradient. Because of that, two layers will have friction, and because of friction, the temperature will go up, and temperature reaches up to billion degree Kelvin. And that's when this addition, this starts emitting radiation. Okay? So what is happening here? Here the conversion of gravitational energy to thermal energy emission is likely to be the origin of observed radiation from emission line galaxies. Now you have started that I told you one thing, that these objects were super bright. Probably this because of this mechanism. Fine. And I'm talking about only the central region of the galaxy. I'm not talking about the whole galaxy. This region is like tiny. Suppose if this whole galaxy is like this room, so this central region will be like this big, or maybe even smaller. Fine. So now you imagine that such a small place are emitting so much radiation. Got it? All right. This I already told you. Now, since the central region or nucleus of the galaxy is active, it's emitting lots of radiation. Active means emitting lots of radiation. So that's why we call such central region as active galactic nucleus, or AGN, and such galaxies are called active galaxies. Okay? Now you understood? I have not yet told you how those emission lines are coming. You will see. But you understood by now what is an active galaxy. Fine? And what is the physical mechanism that leads to the observation of very bright radiation that we see from such objects. Clear? Okay? Alright. So let us see another video. This is a schematic cartoon. Okay? Before we see the video, let me tell you one more information since it is there. AGNs are 1,000 times more luminous than the entire Milky Way, and this much energy is being released within a region which is approximately the size of our solar system. Okay? And now I will tell you later, maybe in the next class, very briefly, that there are some special type of AGN on this icon. They emit more energy per second than that emitted by the sun in its entire lifetime. Okay? That's what we do. Most powerful. We'll see tomorrow. Alright. So let us see a video. I'm not sure it will work. At least now it will not work. Okay, so let us see the video somewhere else. Fine, we are done with this, and then we'll go with this. Fine, shall we start? So let us take a picture. What you are seeing here, it looks like a normal galaxy. In the galaxy, let us how you some Okay, we just had a tour of an active galaxy. So see, this means they look like a normal galaxy. They are like normal galaxy. Overall, they look like normal galaxy. But the speciality is that when you go to the center, from outside, these galaxies will have planets, stars, X-ray binaries, supergiants, everything they will have. O, B, A, F, G, K, M. थोड़ा याद आया? Okay, everything they will have. They will have giant moon clouds. But on top of that, they have a central region just for it. Okay? So now let us see very quickly in the next 15 minutes or so the different components of an active galactic nucleus. Means whatever we just saw, let us understand them. Fine. Any question so far? No question. Very good. Yes, you see not here. Okay. AGN components. Fine. So everybody will agree the first component will be central supermassive black hole. In astronomy, when we say supermassive, we typically we mean that the mass is typically more than 1 million times mass of the sun. Supermassive. If it is less than that, and suppose if it is larger than say 1,000 solar mass or say few hundred solar mass, we call it intermediate mass black hole. And so far we have not found many observation evidence for intermediate mass black hole. We know stellar mass black hole. Stellar mass black hole means the black hole whose mass is like 5 solar mass, 10 solar mass, 15 like that. On the other end we see 1 million solar mass black hole, which is supermassive black hole. Or we know up to 10 billion solar massive black holes. I will work on all those things. Fine. See, this is black hole. I'm showing you a black hole today. Be happy. You see, today you witnessed. Today you saw black hole. This is black hole. I was talking about there are several observational evidences now for the existence of supermassive black hole. Imaging with the Event Horizon Telescope. So this picture is what we expected from our theory. This is an idealized simulation. Okay, this is kind of structure we assume if the black hole is somewhere here. This is the infalling gas only. Fine, and this is what we saw. How nicely it matches. Okay, so that's how you like a support theory with observation, or you explain observations with theory. Einstein predicted this 1950. It took us like more than 100 years to reach to that level of like instrument sensitivity to detect those features. Fine, okay. Then these black hole had somewhere like 1 pixel in this picture. You cannot see it now because it's too tiny. Its size is too tiny. You can calculate. You already had general relativity class, so you can calculate the Schwarzschild radius. G. What is the formula? G by c square. Is it correct? So if you know m, you can calculate corresponding Schwarzschild radius. You will find it like for even for a 10 to the power 6 solar mass black hole, this radius will be like even this Schwarzschild radius will be small, very small compared to the distance scale that we have. For example, suppose if the sun will be a black hole, its radius will be 3 kilometers. Fine. All right. Gravitational wave detection. This is another observational evidence supporting the existence of black holes. Fine. Okay. We understood that in Asian components, there should be a black hole at this. This is first thing we understood. All right. The typical mass of a black hole residing at the center of galaxies is about 10 to the power 6 to 10 to the power 10 solar mass. Means 10 million to 10 billion. In fact, from theory also you can calculate what could be the upper limit of the mass. We cannot calculate, but people have tried to calculate for the stability of the system. No, black holes can grow, but we have not seen any 10 to the power 15 solar mass black hole. We have never. We have found this number is like touching the roof somewhere around 10 to the power 10, 5 into 10 to the power 10, 6 into 10 to the power 10. But we have never found any black hole 10 to the power 11 solar mass or 10 to the power 12 solar mass black hole. So there is some cap. I don't know why. Maybe it may have something to do with how black hole. Okay. Fine. Accretion disk. You need accretion disk also. Okay, that's what we are doing. We are trying to understand the different components of that central region. What are the different things present there? Based on our observational evidences. Black hole, second is the accretion disk. This accretion disk is formed by infalling matter onto the black hole. Let me show you an accretion disk. It took me hours to make this image. This cartoon. Not hours, but half an hour. Okay, this is an accretion disk. And if you recall, I already showed you this picture some time back. Nobody remembers. This is the accretion disk of a protostar. Before the star reaches main sequence, it starts accreting a matter, forming an accretion disk. Wherever there is a compact object, and if there is a matter inside surrounding, the matter will be like a drag, like pulled towards a compact object, it will form this. So you have a small scale, you have a protostar. On larger scale, we have active galaxy. Fine. And this, in this case, this greenish bluish disky shape structure you are seeing, and this orangish shape. See, because at the central region you are overwhelmed by the radiation. It is so bright. But this overall structure is the accretion disk. So now you understood that in one part of that video. Okay. Together with the black hole. Light means black hole and accretion disk. Collectively, these are called the central engine of an active galactic nucleus. Because this is the engine which is producing energy. If there is no black hole, no accretion disk. There could be a black hole without an accretion disk. If there is no matter surrounding the black hole, what guy will do? Like in our own Milky Way, there is not enough material surrounding the black hole. So our black hole in the Milky Way is passive. Simplicity, quietly waiting for something to come. Come, then we need. Okay? Fine? So together it's called this black hole and the accretion disk, they are called central engines of an AGN. The typical size of an accretion disk is around 10 to the power 12 kilometer, which turns out to be about a few light days. Okay? See, you may be thinking like light days is too much. Just pick this. But compared to the size of the galaxy, it's very, very tiny. Fine. The light takes like some few days to reach from one end to another end. So big region. And you see, not only accretion disk, this entire galaxy like is like held by the black hole. This object. Whole galaxy is held by the gravity of that black hole. Okay? It's like Papaji of a family. He's holding the whole family. Alright. Fine. Now I told you this disk has a multi-layered structure. Means different layers have different temperatures. Every layer is emitting like a black body. So this means overall this structure, accretion disk will emit radiation of a multi-temperature black hole. What I mean to say is that some layer will have some temperature, there will be corresponding some black body emission. Some other layer will have some other black body emission. Some other layer will have the hotter layer will have peak coming toward the higher frequency. Isn't it? Kabilan, understood? I will ask a question. Okay, but you see, we see the sum of everything. So we see what is the sum of all the layers. And in fact, you know that you can calculate this radial dependence of temperature. People have done the calculation. This is a very good equation. Okay, so it turns out that the radial dependence of temperature is given by this equation, where RSCH is the Schwarzschild radius. This means now you understood that it is this temperature also depends on the mass of the black hole. Bigger the black hole, bigger the accretion disk. Chotu black hole, chotu accretion disk. Fine. Got it? Now LD is the disk luminosity. The overall luminosity of the accretion disk, that's what we get, that's what you want to get. Eta accretion is the efficiency of accretion, which could be up to 30%. Typically, we take 10%, typical number. Because this accretion efficiency also depends on whether the black hole is rotating or not, means whether we assume the black hole to be rotating or not. Rotating black holes are called Kerr black holes, and non-rotating black holes are called Schwarzschild black holes. Fine? Because when you have a rotating black hole, the picture becomes more complex. Okay? Sigma m is the Maxwell-Boltzmann constant. R is the distance of that particular layer from the center. Okay, so you know that you can write a simple program to calculate the R radial dependence of the temperature. So you can do it. It's fun if you have free time, try to do it. You see how it looks like. And then you can calculate the flux coming from that accretion disk. And you see, you must have seen this formula. Okay, you have seen this formula. Planck equation, Planck's law. Mu1 to mu2, this means where you are standing, Suppose accretion disk is there, I am standing here. So two edges of the accretion disk will be forming some angles with. So this mu and mu2 is the cosine of those two angles. So this means this radiation pattern that we see from accretion disk, it is not isotropic. It is anisotropic. Anisotropic means it depends on your viewing angle from where you are observing that accretion disk. Corresponding radiation pattern will be different. Fine. All right. Two things we have finished. What next? X-ray corona. Okay. Why do we need X-ray corona? Because when we observed these active galaxies, we found them with bright X-ray emitters. They are bright in X-ray bands. Okay. But the problem is that accretion disk is too cool. Cool means in sense to produce X-rays. To produce X-ray, you need temperature of the order of 10 to more 10 million degree Kelvin to even higher. Fine. So accretion disk is too cool to produce X-rays on average. So this means we need something else which is emitting X-rays. But accretion disk cannot emit X-rays. Possibility is not emitting X-rays. So what people did, they put up some plasma, something on top of that accretion disk, and they called this is X-ray corona. And telling this its temperature is 150 Kelvin, up to 150 Kelvin. You can calculate what is the temperature in Kelvin corresponds to 150 kiloelectron volt, not 150 Kelvin. 150 kiloelectron. 3 by 2 kT equal to H. Yes, E equal to H means E equal to 3 by 2 kT. Fine. Now, what is this corona? Basically, this corona is a low density magnetized plasma. This is what typically what we see in solar X-ray corona. Okay, you might have heard the word coronagraph. Out like during the solar eclipse, we used to see solar corona. The outer globe. This is the at the outer layer of the sun. This is like a low density magnetized plasma without low density. Okay, and its temperature is very high. You might have seen some. I don't think I have some cool photos of this X-ray image of the sun. Maybe you can search in Google X-ray image of the sun. Okay, and you will see nice like a glowing orangish loops. Also, you will see this structure is called corona. So people have proposed that some sort of this must be present in active galaxy also. We have not observationally we have seen this feature because they are so small inside and these objects are so distant, we cannot resolve them. And also why we cannot see them, because the radiation is so much radiation is coming that we cannot see anything else. I showed you an example of car. The headlight is so bright you don't know who's sitting behind. Fine. Now X-ray, you know that this is a corona. It is emitting X-ray radiation. Suppose you are an observer somewhere here. Okay, don't go for the side of the observer. Okay, suppose you are an observer, so you will be getting some radiation coming directly from the corona, and some of the radiation may be falling onto the accretion disk and it may get reflected. So you will also see a reflection spectrum. You are expected to. Fine. See, these are the theoretical models. Observation we have not seen them, but theoretical model. And then we will see whether these theoretical models can explain the observation that this is what we get. Fine. So if you talk about the typical X-ray spectrum of an AGN, it can have soft X-ray bump. Soft X-ray means I am talking about below 1 kiloelectron, and means the radiation is higher. This is bump, which we call soft X-rays or soft X-ray bump. And people have proposed that probably this reflection spectrum is probably one of the possible reasons that this leads to emission. We do not know. It's a model-dependent explanation. In some cases, we do see iron K-alpha line. Emission line means we are seeing emission line in X-rays. Okay, K-alpha means iron has K shell, and I will leave you to explore further what is K-alpha. But this is like a transition shift. It's ion transition from the K shell and onwards. So the energy is coming around 6.4 kiloelectron. Okay, so we see a bump. This means the matter which is surrounding this very central region of the active galaxy. There could be the iron also present. Possible. but it is in a very ionized state. Iron also in the ionized state. Fine. And here we are in extreme gravity. So observationally, what happened? But I will tell you, we have seen soft X-ray access, which gave us idea about the reflection spectrum. We do see iron K alpha line several spectrum of several EGN, which tell us about the behavior of matter in the immediate surrounding of the black hole. Means what, how matter behaves just before falling onto the black hole. So there is a model dependent calculation, but you can also calculate the black hole state if you can determine the width and the strength of this iron K. Okay, and then we add high energy, we have a component as it names in the reflection hump. So this means this bump is people have also proposed to be explained by this reflection spectrum. I am not a super expert in this topic. If you want to know more about it, probably see there. You know, one teacher will be teaching here, Professor Gulab Devangan. He is expert around. He will teach you X-ray tomorrow. So catch him if you want to know more about X-ray. Corona, fine. Then I am going to talk about the lines that we were observing in the first case, emission lines. So there is something called broad line region. What it is? People have proposed there are clouds of dust and gas. You remember in the video? Some dusty patches of clouds, they were orbiting around the black hole. And their orbital velocity is about 3000 to 10,000 kilometers per second. These clouds of gas and dust, they orbit around the planet. Fine. Video I showed you, cartoon also I'm showing you. Pink color clouds. Fine. The typical distance of these clouds are about 10,000 light days. Okay. Typical electron density about 10 to the power 8 electrons per centimeter cube. So this is a density. Okay. And what happens? These broadline region clouds, they intercept the accretion disk radiation and re-emit in the form of emission lines. So these clouds are nothing but your hot gas. Fine, and since they emit broad emission lines, that's why we call this region where these clouds are there. This region is called broad line. So the emission line that we are seeing from active galaxies, they are produced by these PLR clouds. Okay, so now we have one more information. Fine. If from imaging we have not resolved those features, but from spectrum we can get the idea. And one interesting thing here is that these lines you see, they do not look like one delta function. They look like a broad lines. Okay, you see there's some width. And this width happens because of the something called Doppler broadening. So what is happening? See, in this orbiting clouds, some clouds will be moving towards you and some clouds will be moving away from you. So the cloud which will be moving away from you, their line will be slightly redshifted. Okay? And the gas which is moving towards you, that the line emitted by that gas cloud will be slightly shifted. Fine. And this we have observationally seen. This is the M87, the first that galaxy for which we got the first event horizon telescope image. And from Hubble Space Telescope, we were able to resolve lines which are redshifting and which are blue shifting. But since the other active galaxies are very far, so we cannot resolve them. So what we see some of everything. That's why we see overall one broad. Okay, we see that's how we explain one by one on the observation that we get. Okay, all right. Now let's go to something else. Something called narrow line vision. This is also an alien component. What it is, as the name suggests, otherwise the broad line vision is a narrow line vision. So what is, these are the distant clouds orbiting the central engine with relatively low velocities. So their velocity is typically few hundred to 1,000 kilometers per second. Why they have low velocities? Who will tell me?
And radially away from the.
Yeah, they are far. V proportional equal to square root of gm by r. R is larger, G is less. So since they are far, so gravitational pull is less, so their velocity is lower. Isn't it? Fine. Okay, how do we know that the velocity is 1000 km per second? Means how do we measure this velocity? From the width of the line. Because this width is because of your velocity, orbital velocity. Okay? You got it? So if you remember in the first class when I was teaching you Python, I showed you one optical spectrum, and if you recall, I was fitting some line with Gaussian function and all. I was trying to calculate the width of it. Because higher the mass of the black hole, larger the velocity, broader will be the line. So this means if we can measure the width of the line, that will tell us about the mass of the black hole. So that's how we measure the mass of the black hole in galaxies, active galaxies. Fine. So see, this optical spectrum provides so many information. Got it? And you understood that those emission lines that I was talking about, they are produced by broad line region. And broad line region itself is getting radiation from the accretion disk. Fine. So if you can determine the luminosity of those lines, that will, by applying some more physics, you can calculate the luminosity of the broad line region. Because the broad line is emitting that line. And once you know the luminosity of the broad line region, you can calculate the luminosity of the accretion disk. You see, the same optical spectrum will give you the mass of the black hole as well as the luminosity of the accretion disk. These are the two primary parameters to constrain the property of the central line. So that's all. नहीं समझ आया कोई टेंशन की बात नहीं. Thought about it. Think. Thought mode.
Sir, isn't the clouds like patches of clouds? They are not uniform.
No, they are not uniform. So that's what we believe that their distribution should be uniform. They may not be. You see, for the calculation purpose, okay, if we start assuming them as different patches, then the calculation becomes extremely complex. Because every patch will move with its own velocity. Then it becomes super complex to do the mathematics. So what instead we do, we assume that this broad line region is a spherical shell. This is just for simple calculation purpose. What? Okay? It's an assumption, simplification. This I already told you, AGN distance is around 1000. So narrow line region is about 1000 light years. 100 to 1000. 100 to 1000, not 1000. You see here electron density is relatively less. 4 orders of magnitude lesser than that in broad line region. Now interesting thing is that these narrow line region clouds also intercept the radiation emitted by the accretion disk. So you understood here accretion disk is like your bottom. It is throwing radiation in all the directions. Broad line region clouds also intercept the radiation and they emit lots of emission lines. Narrow line region also they also intercept this accretion disk radiation, and since their velocity is less, so Doppler broadening will be less. So we will see very narrow emission lines. But you know that whether it is a broad line or it is a narrow line, suppose I am talking about the H beta line. So whether H beta line is broad or H beta line is narrow, it will peak at one wavelength only. So in other words, as an observer, what we are going to see, suppose we have this x-axis, y-axis, you understood. So broad line will be something like this, and narrow line will be something like this. So observationally, we will see something like this. You understood? Everyone understood? This is what I was doing when I showed you that photo, when I was fitting with the different Gaussian components. So I'm able to decompose the spectrum in broad line component, narrow line. And these things, what I'm telling is very easy. It also depends on the quality of the data. You have very good quality data, you can really resolve those features. You can determine the width of the narrow line, width of the broad line, that will give you other physical information. Okay? Okay, here the density is so low in this narrow line region that even forbidden emission also takes place. Everybody knows forbidden lines. You don't know? Who knows? Forbidden lines, forbidden emission. Forbidden emission, you don't know? Homework. Only 12:20, so it's homework. Read forbidden lines. Okay? Read about it. What is forbidden emission light? Fine. Then there is something called molecular torus. Torus we have observationally seen. You remember this photo? That's what we first saw when we were reaching the central region. Okay? This dusty donut shaped structure. These people have proposed this is called torus. Okay? And from the Hubble Space Telescope imaging, we have seen this torus shaped structure. And this is the cartoon I'm showing you the cross section. You understood like a donut shaped structure. Vada. Okay? I'm showing the cut off there. Fine? You see everything is there. This is everything I'm talking only about the AGN. Nuclear part. Typical size is a few hundreds of light years. Typical temperature is around 300 to 1500 Kelvin. You understood the temperature is too low for the lines. So that's why this torus primarily emits continuum radiation, and you can calculate the wavelength corresponding to this temperature. It will come in the infrared. So this torus is like you can say it emits primarily in the infrared. Okay. What will happen if the temperature will be higher? Okay, I will tell you what will happen because this torus is basically gas, dust, etc. If the temperature will be higher in this torus case, this gas, this dust, the dust will evaporate. So you can calculate what is the sublimation temperature for say granite. I talk about granite when I'm talking about the giant molecular clouds. Their temperature 15 Kelvin, so it's too cold. But here the temperature is at 2000 Kelvin. Around 2200 Kelvin is the sublimation temperature for granite. So dust will evaporate. So, but since we do see torus, this means temperature is less. Otherwise, it will be evaporated by normal. Alright, this I have already explained you. See, all these things are getting energy from the elements. And they are reprocessing. Something is reprocessing in line, something is reprocessing in radiation, infrared radiation. And this torus is very crucial AGN component for their classification that we will study tomorrow. Okay, now coming to the last part, which is my favorite. Favorite thing always come in the last. Jets. Okay. What is a jet? Collimated, relativistic, bipolar flow of the plasma blobs shooting out of the plane of the emission disk. So you can imagine like this jet kind of structure in which plasma blobs are traveling with relativistic speeds. Like I will demonstrate one example. You know, this is the engine of a jet. This is also a jet. This is a fighter jet. You see this knotty structures. So you can get some similarity with the kind of jet we see in AGN. Okay. That I will tell you. Just to give you an idea about the size. The typical size of these plasma blobs, it is like a few light hours to a light day. So you now imagine a plasma blob as big as where the light requires movement, let's say 10 hours to reach from one end to another end. How big it will be? Okay, and this big thing is moving with the speed 0.99 c. Only a black hole can do this magic. So wherever in the universe, whenever something unusual is happening, you should immediately understand the black hole. That's the only thing. Okay. Now I told you collimated. This means it remains like a laser beam. So how it remains? See, the plasma, like this plasma, like you have a charged particles, etc., electron, protons, positron, etc. They are moving along the jet. So they have a natural tendency of expanding. Of course. But it remains collimated, so you need something which can compress it back. That job is being done by magnetic. Okay? Fine? Okay? If you want to see, I can show you some simulation how this magnetic field actually behaves very close to the central. I have this video with me, but we are already late, pretty late now. Okay, this size could be as large as up to billion light years, megaparsec scale. This means these jets can come easily, they can come out of the whole galaxy. Rest of the thing is within the tiny part of the galaxy, but these jets can come out of the galaxy. They're so large. Okay? But the good thing is that these jets are observed only in about 10% of region, and even lesser. So if you observe 1,000 active galaxies, only you'll find in a few like 10, 20, 50 regions have these jets. Okay, these jets are very strong radio emitters. This means they are bright in radio because of a process called synchrotron. पढ़ लिया आप लोगों ने, पढ़ा है ना synchrotron radiation. ठीक है, I will also teach tomorrow a bit of that. But the question is how jets are launched. This is the first philosophy comes into our mind. Like, okay, such a interesting thing. How it originated in its first place. Okay, so this we understood. But we know that these jets are launched in the very central region of that galaxy. So this means it has something to do with the black hole and the accretion disk and its interplay. Okay, but observationally we have known that what triggers the launching of electricity jets. Now I will let us finish this lecture by watching some cool pictures. Cool pictures means the real picture. I am not going to show you some cartoon. Okay, let us see a picture. So this is a composite image. The bluish blackish color you are seeing, this is an infrared image. So the white spots you are seeing, basically these are galaxies, stars, etc. And this yellowish orange thing you see, I am telling this is a jet. This is the galaxy somewhere here, and it is emitting this jet you can see. When you ask why it is not continuous, it might be continuous, but the radiation from this part might be very faint to it, which is not seen. I'll tell you one more possibility here is that this is also possible that the galaxy also is active the center here, which is not even 1 pixel in this image. It might have emitted some jet some millions of years ago. Okay, and then it switched off. And now it has restarted jet activity. So, but the point is that you have already thrown something out. That material is kept traveling. The black hole became dormant for some time, and now it is restarting its activity again. But that jet is still going. Okay, fine. So you see, this is this jet could be the remnant of the previous experiment. Could be. Now, but I do not want to talk about all these things. I want to talk about the distance. This end-to-end length is 16 million light years. Okay, and for this, and basically I show you a picture of the largest scale jet ever observed in our history of astronomy. And when people try to calculate the mass of the black hole at the center, it came around like 12 billion solar mass black hole. Of course, you are keeping something so far, you need something super powerful at the center. Isn't it? Okay, let us see one more photo. Okay, but before see, I will give one idea. This is the size of Milky Way. Now you compare. Our whole galaxy, our entire galaxy is that size you seeing that inside that circle. Now you compare the size of the planet. Okay. Santos only is our minute. Anyway, I'm done. Okay, this is again a composite image. Okay, colorful thing you are seeing which you wanted to see, orangish, yellow, reddish color. This is the jet. This is a radio image, and then bluish and this background image you see. This is your optical or maybe infrared image. So you see, jets are not always a straight line. They are like a water hose. You throw water from a pipe. There's some flickering, and everything happens in the sky. And if you see the central part of that, you see this bluish, that blob. This is the host galaxy, whole galaxy. Elliptic, it's an elliptical galaxy. This is a real image. Okay? And you see that's how jets are launched. One more picture. It was like somebody has opened a tap water. It's just coming out of that. Okay? And here a plethora of it. This is the optical image of the 3C273. I'm sure you might have forgotten that when I showed you one normal galaxy picture and one active galaxy picture, and in that active galaxy picture, there's something coming out of that thread. This is that jet. If you block the central bright part, you can see this jet. Okay, this is the radio image. You see the whole galaxy is this one point, and then you see the size of the jet. Okay, and you see this is the high resolution image, Hubble Space Telescope image of the jet. You see these knotty structures? These are the moving plasma blocks. So people have observed them for different times, and then they calculated the velocity with which they move. So that's how we can measure the velocity. That's how we can determine the velocity of this. Okay, and then you see this is the jet of the M87, 5,000 light years, and this was first imaged in 1907 or 1908, and that time they thought there is some star from which some stray light is coming out. Okay, and there is another picture. You see this glowing, this block. This is the galaxy, optical image. And when you overplot the radio image, then you will see this jet structure. So this means if you take a look at this galaxy from your own naked eye, you will not see jet. For that you need radio goggles. Okay, everybody is happy? That's it. Thank you. I think if you have more questions, you can talk to me later. Please go for lunch. I will quickly take if there are any very quick questions from the online participants. I'm not hearing any question so far. So I presume all is well. Prakash, is there any question?
No, Vaidehi, I don't see any.
Perfect. Okay, so then I will close the Zoom session. Now I will stop the screen sharing. So thanks everyone for joining, and then we will talk further. Okay. I have closed the Zoom. I have closed the Zoom. I have closed. Okay, I have closed the Zoom. Aniket, shall I close the Zoom here or just keep it? Close it, no? Okay. Do you have any quick question?